The majority of electrical faults faced by automotive technicians today result from a change of resistance within a faulty circuit. Resistance is an unwanted problem caused by corrosion, poor terminal tension, internal component failure, or the effects of heat. Too much resistance and the circuit simply won't operate. In this module, you'll learn the application of voltage drop theory and some practical troubleshooting using this technique. If you're unfamiliar with voltage drop, we recommend that before you watch this module, you check out our other training videos in the series. For most automotive circuits, a voltage drop test procedure can be performed with a digital voltmeter. A digital storage oscilloscope is more practical for high-speed circuits like ignition, injector, and communication systems. It's important to remember that a voltage drop check is a dynamic circuit resistance test. This simply means the circuit needs to be switched on when performing the test. Remember, there'll be no voltage drop across the load if there's no current flowing. If we're testing the horn circuit, the horn needs to be activated when performing checks and measurements. Or if the brake lights don't work, the brake pedal must be depressed before any measurements are taken. Prepare the voltmeter by setting the scale to millivolts. We use a millivolt scale because most digital meters display an over limit indicator if the voltage exceeds 500 millivolts or half a volt. This is the generally accepted maximum allowable voltage drop for a circuit. Review the schematic for the circuit under test and be sure you understand the current path and how the circuit is controlled. Think of the circuit in three parts: the voltage supply, the load, and the ground path. The voltage supply is that part of the circuit that runs from the battery positive terminal to the upstream side of the load. The load is the component doing the work in the circuit and will be a critical test point. The ground path is the part that runs from the ground side of the load to the chassis and then back to the battery negative terminal. When performing the test on a vehicle, attach the negative meter lead to the positive battery terminal as close to the post as we can. On our test board, we'll use the voltage source point. Next, we'll place the positive meter lead on the power side of the load. Again, attach this lead as close to the load as possible. When performing this test on a real brake circuit, a long extension test lead, like this one, may be required to reach from the front of the vehicle to the rear so each test can be performed correctly. It's important to remember that this test is only going to check the dynamic resistance of the circuit between these 2 points. Since everything in an electrical circuit offers some resistance, the meter will and should display a small voltage reading, less than 500 millivolts, when the circuit is switched on or operating. If the meter displays a perfect 0 volts, that indicates that there is no current flowing in the circuit. If the meter indicates an over limit reading, switch it over to DC voltage for a more accurate display of the voltage drop. With experience, you'll quickly learn that any problems associated with unwanted circuit resistance will display a substantial reading on the meter. With a substantial voltage drop over the entire circuit, we need to localise the source of the unwanted resistance. This is accomplished by repeating the test at each point in the circuit, working from the load back towards the battery. Move the test lead back toward the battery while watching the display. You'll know when you've passed the location of the fault as the meter reading changes from OL to substantially less than 500 millivolts. The source of the unwanted voltage drop can be identified by this change in the meter value. If the fault is localised between two connectors, focus on any splice joints in this harness section, or points where the wiring passes through a firewall or door frame. Look for pinch points or evidence of accident repair. If the voltage supply has no fault, then it's time to test the ground side of the circuit. Again, if performing this test on a vehicle, move the negative lead to the negative battery terminal. Again, keep as close to the post as you can. If performing this check on a vehicle, Don't place the negative meter lead directly to the chassis earth or ground point. While the ground circuit may use the chassis or body as part of the return, we must always test the integrity of the entire path back to the battery. Next, move the positive meter lead to the ground side of the load. Again, keeping as close as possible to the load itself. Switch the meter to millivolts, operate the circuit, and read the display. If the meter value shows OL, then switch the meter to volts DC. A reading equal to the open circuit voltage of the battery is an indication of an open ground path. Again, this means there is no current flowing in the circuit. The reason we see open circuit voltage is simple. No current flow equals no voltage drop across the load. We're measuring battery voltage the same as if the meter leads are directly across the battery posts. A reading of 0 volts on the ground side also indicates no current flow, but this time the cause is in the load itself, or more precisely, there is an open in the section of circuit between this test point and the last one from the voltage supply side. An OL value displayed when testing the ground path indicates an unwanted source of resistance on this side of the circuit. We can isolate its location using the same method from the voltage supply side. Start by moving the positive lead towards the battery, testing at each side of a connector or splice joint while watching the meter. As soon as the meter value changes from OL to a substantially lower millivolt reading, we have found the fault. Although a rare occurrence, sometimes we may get to the end of the circuit and see no abnormal voltage drop on the meter. If this is the case, the fault most likely lies in the load. A mechanical failure, such as a solenoid that is stuck in one position, or a shorted AC compressor clutch that can no longer build a sufficient magnetic field to engage, will result in a normal voltage drop reading when measured across the load. This value exists because there is still current flowing in the circuit, even though the load is not operating correctly. Today, we used a simple circuit on the bench to demonstrate our testing procedure. If you are serious about learning, we encourage you to do the same. Use a test rig like this one. Change the circuit resistance often while repeating the measurements. Keep this up until you are confident that you have learned the language of voltage drop. Only then you'll be ready to apply this knowledge to real-world challenges, and we'll be here to show you how.